Students, welcome to Sunil's tutorial. I'm Sunil Birwani and today we'll be doing this chapter called as EMI. Today we will first start with Faraday's law of electromagnetic induction. Now last lecture we had seen how you move a metallic frame in a magnetic field. Today we will see how to move a conductor in a magnetic field. So let's consider that you have a magnetic field. This is your magnetic field of induction B. Let's assume that I have a conductor placed in this magnetic field. Right? Let's assume that the length of the conductor is dx and it's being moved outwards, right, with the velocity of v. Let's write this much down first. We'll say consider a straight conductor. Consider a straight conductor move with uniform velocity at right angles to a uniform magnetic field. Uniform magnetic field. Now, in that case, an EMF is going to be induced. So let us assume let B be the induction. Let's assume that B is the induction of the magnetic field. Let's also assume that L is the length of the conductor. V is the velocity with which it is moved, velocity of conductor. Right? Now, in that case, let's assume that dx is the displacement in time t. Dx is the displacement of the conductor in time t. Now, in that case, I can say that displacement is nothing but velocity into time. Displacement is going to be equal to velocity into time. Displacement is going to be nothing but velocity into time. Now, let's assume that if dA is the area swept, if dA is the area swept in time dt, right? If dA is the area moved, then I can say area is nothing but length into breadth. That means I can say that area is L into dx. Area is nothing but length into breadth, which I can say is nothing but length. Dx we had already said is nothing but v into dt. So dx can be written as v into dt. Now, if d phi is the change in the magnetic flux, d phi is change in magnetic flux, right? If d phi is the change in magnetic flux, then I can say that d phi is nothing but magnetic induction into area, right? In which case I can say that magnetic induction area we found out is LV dt, right? Now, in that case, the EMF induced, how do I find out the EMF induced? EMF induced is nothing but the rate of change of magnetic flux. EMF is nothing but rate of change of magnetic flux. right? In which case I can therefore say that EMF induced is nothing but BLV dt upon dt, right? So therefore I can say that EMF induced is going to be nothing but BLV. So that is the EMF induced by a conductor of length L moving with a velocity v in a magnetic field of induction B. Right? Do we get this in here? So once you have this, on the basis of this, then you can state your Fleming's right hand rule. Fleming's right hand rule. Now Fleming's right hand rule says that stretch the thumb and the first two fingers thumb and first two fingers in such a way of the right hand, in such a way that they are mutually perpendicular to each other. They are mutually perpendicular to each other, right? In which case, if I turn, guys, this is mutually perpendicular to each other, right? The thumb and the first two fingers are mutually perpendicular to each other. Now in that case, turn the hand in such a way such that the forefinger points towards the direction of the magnetic field, right? And the thumb points towards the motion of the conductor. This is the direction of the magnetic field and this is the direction of the motion of the conductor. In that case, then the middle finger will indicate the induced EMF. So the induced EMF will be in this direction. This is going to be the direction of the magnetic field. This is going to be the direction of the motion of the conductor. This is the direction of the magnetic field. If I have a magnet here and if the conductor is moving in this direction, then the EMF induced will be in right angles to it. Fine? Do you get this? Each other. Turn the hand such that the forefinger points in the direction of magnetic field and the thumb points in the direction of the motion of the conductor then the middle finger indicates the direction of induced EMF. That's your Fleming's right hand rule. Fine, do we get this in here? Right? Once you get Fleming's right hand rule, now let's see what is inductance, self-inductance and mutual inductance. Right? Now, what do we understand by self-inductance or self-induction? Now, we had said that when electric current flows through a coil, it produces a magnetic field in the space around it, right? And the magnetic flux of this field is linked to the current flowing through the coil, right? If there is a change in the current, then flowing through the coil, then there will be a change in the magnetic flux flowing through the coil, and by Faraday's law, EMF is induced in the coil. Suppose if I have a coil, I have current flowing through a coil. Right? Current flowing through the coil. This is current I that flows through the coil. Right? Now, when the switch is turned on, current I flows through the coil, and therefore there will be a magnetic field that will be produced around the coil. So there will be a magnetic field that will be produced around the coil. Now, if the current is changing, if I plug the switch on and off, then the current will not be a steady current. Hence, there will be a changing current. The changing current will produce a changing magnetic flux. And by Faraday's law, if there is a change in the magnetic flux, it produces an EMF. Thus, this EMF is induced in the coil due to the change in the current in the coil. This phenomena is called as self-induction. And the EMF induced in such a way is called as self-induced EMF. So thus, the production of EMF in a coil due to the change in the current in the same coil is called as self-induction. The production of EMF in a coil due to the change of current in the same coil is called self-induction. So when current changes in a coil, there is going to be an EMF induced in the coil, and that if the current is changing in the coil and EMF is induced in the same coil, then that is called as self-induction. Now, let's try to understand the direction of the EMF induced. The direction of the EMF induced in this coil is going to be given by Lenz's law, right? What does Lenz's law state? It states that the direction of the induced EMF will be such that it will oppose the change in current. The direction of induced EMF is given by Lenz's law, right? Lenz's law states that the EMF induced will change the will oppose the change in the current, and thus if I close the switch, current will flow in a particular direction, and the direction of the EMF induced in this case will be such that it will oppose the increase in current. That is, the induced EMF will be in a direction opposite to the applied voltage. Lenz's law. If the switch is closed, current in the coil increases from 0 to I, right? In that case, the direction of the induced EMF induced EMF is such that it opposes the increase in current, right? In that case, it opposes the increase in current. That means the induced EMF will act in a direction opposite to that of the applied voltage. Therefore, the induced EMF will act in a direction opposite to applied voltage. right? Same way on the other hand, if I switch off the plug, in that case current in the coil will decrease from maximum to 0, right? If the current in the coil decreases from maximum to 0, then the EMF induced in the coil will be such that it will oppose the decrease in current. That means it will act in a direction, in the same direction of the applied EMF, right? So I can say that if the switch is open, then current decreases from I to 0, right? Then the direction of the induced EMF is such that it opposes the decrease in current. That is, therefore the induced EMF will act in the direction same as the applied voltage. Fine, do we get this thing here? Now, it is also found that the magnetic flux linked with the coil carrying a current I is directly proportional to the current in the coil. How much will be the change in the magnetic flux, or how much will be the magnetic flux that will be produced due to current flowing in the coil will depend upon the current that is flowing through the coil. If the permittivity of the surrounding is 1, I can say also flux is directly proportional to current, right? The flux that will be produced in the coil is directly proportional to the current flowing through the coil. Obviously, more current flowing through the coil, more magnetic field, hence more number of lines of force. Less current flowing through the coil, less magnetic field, therefore less number of lines of force. Therefore, I can say that flux is directly proportional to current. Therefore, I can say that flux is equal to Li, where L is a constant, and depends on the value of L depends upon the number of turns in the coil, and it depends upon the geometric property of the area, shape of the coil, geometric properties of the coil, right? These are the two factors. Now, if current flowing through the coil changes, the magnetic flux will also change, and a changing magnetic flux induces an EMF. If current flowing through the coil changes, then flux is linked to current. If current changes, then flux also changes, and a changing flux produces EMF. I can say therefore EMF is induced in the coil, right? Therefore I can say that EMF is the change in flux with time, and by Lenz's law the EMF will be such that it will oppose the motion of current. Therefore I am going to put a negative sign to show that the direction of EMF and flux are going to be opposite. Now this can be written as minus d by dt. Flux is nothing but Li, right? Therefore I can say minus L di by dt. So EMF is nothing but L into di by dt. The negative sign in this expression indicates that the self-induced EMF always opposes the rate of change of current, right? And L is the constant, and it is the constant of self-inductance of the coil, right? In terms of magnitude, E will be equal to just L di by dt. E is going to be equal to, in terms of magnitude, E is going to be just L di by dt, right? Now, if di by dt is 1, if rate of change in current is 1, then I can say that E is equal to L. The EMF induced is equal to the constant, self-inductance constant, right? Therefore, I can say the self-inductance of a coil is equal to the EMF induced in the coil if rate of change of current is unity. Right? That means I can therefore say that L is equal to E upon di by dt, right? Units, in terms of units of L will be nothing but units of E, which is volt, and change in current upon time. Current is ampere per second. So units of L will be volt second upon ampere, right? Volt second upon ampere, one word for that is Henry. Right? Therefore, the inductance, self-inductance of a coil is measured in terms of Henry. Right? I can say that therefore, self-inductance L of a coil is 1 Henry when an EMF of 1 volt is induced in the coil when the current changes, when the current in the coil changes at the rate of 1 ampere per second. Right? So that is what is self-inductance, right? So this was when you have a coil and you have EMF induced in the coil and you have current flowing through the coil which produces an EMF in the coil. Now, instead of one coil, let us try to see two coils. Let us try to see mutual inductance. Suppose if I have two coils placed close to each other. Right? Let's assume I have current I flowing through coil A. Right? Now, if current I is flowing through coil A, a magnetic field is going to be produced. There will be some magnetic flux produced. Coil B will lie in that magnetic flux. Now, if the current in coil A changes, there will be a change in flux, right? And hence an EMF will be produced in coil A, right? Since coil B will also be subjected to a changing flux, because coil B lies in the magnetic field of coil A, since coil B is also subjected to a changing flux, therefore an EMF will be induced also in coil B. change in flux produces EMF. B is going to be subjected to a change in flux because it lies in the magnetic field of A. Therefore, an EMF will be produced in coil B, and that is called as mutual inductance. I am producing EMF in A, and you have automatically EMF induced in B. Fine, do we get this thing then? Let's write this down. Consider two coils A and B placed near each other. Right? In which case, if current flows through coil A, if current flows through coil A magnetic field is produced in the space surrounding it. A magnetic field is produced in the space surrounding it. Right? Since coil B lies in this magnetic field, since coil B lies in this magnetic field, the magnetic flux produced by A is also linked with coil B. The magnetic flux produced by coil A is also linked up with it, right? So thus you will have a magnetic flux that will be produced also in coil B because it is placed in close proximity with coil A. Now if the current in coil A changes, if current in coil A changes, right, there will be a change in the magnetic flux associated with coil B. There will be a change in magnetic flux associated with coil B, right? Now, change in magnetic flux will result in EMF. As a result, an EMF will be induced in coil B. Right? Now, the EMF that will be induced in coil B by Lenz's law will oppose the change in current in coil A, and by Lenz's law, this EMF will oppose the change in current in coil A. It will oppose the change of current in coil A, right? This phenomena in which the change in current in one coil induces an opposing EMF in another coil is called as mutual inductance. So I can say therefore, how do I define this definition? The phenomena in which change in current in one coil induces an opposing EMF in another, in the neighboring coil, is called mutual inductance. Right, so do we understand what is mutual inductance? It is nothing but the production of EMF in one coil due to the changing current in some other coil. Right? Now this phenomenon, thus in the phenomenon of mutual inductance, the two coils are magnetically linked. If instead of coil A, the current in coil B is changed, then obviously an EMF would be induced in coil A. So in this way I can say EMF in one coil is directly proportional to the rate of change in current in the other coil. I can say therefore the EMF induced in one coil is directly proportional to the rate of change of current in another coil. That means I can say EMF is directly proportional to di by dt, right? Therefore I can say that EMF is equal to m times di by dt, right? I'll put a negative sign here where m is called as the coefficient of mutual inductance. The negative sign indicates that the EMF opposes the change in current, right? M is called as the coefficient of mutual inductance. If di by dt is equal to 1, if the rate of change in current is 1, then in terms of magnitude EMF will be equal to m, right? Thus mutual inductance between two coils will numerically be equal to the EMF induced in the secondary coil when current in the primary coil changes, right? The SI unit of mutual inductance is Henry. The SI unit of M is Henry, right? Thus, what is mutual inductance? Mutual inductance between pair of coils. Definition of mutual inductance. Right? What is mutual inductance? Mutual inductance between a pair of coils is said to be 1 Henry. Between pair of coils is said to be 1 Henry. Mutual inductance between a pair of coils is said to be 1 Henry if an EMF of 1 volt, guys, EMF of 1 volt, if an EMF of 1 volt is induced when a current 1 volt is induced in one coil, when a current changes by 1 ampere per second in another coil or neighboring coil. Fine, do we get this thing here? So if the rate of change of current in the neighboring coil is 1 ampere per second, and if the EMF induced in the first coil is 1 volt, then the mutual inductance is said to be 1 Henry. Right? On the basis of this, you have a device made which is called as a transformer. Now, what do we mean by transformer? A transformer is a device that is used for converting a low AC voltage into a high current, high alternating voltage, and vice versa. So basically a transformer is used for voltage conversion, right? And it is used for voltage conversion of an AC voltage. right? It is used to convert a low voltage into high and similarly a high voltage into a low voltage. So how do I define a transformer? It is a device used for converting low alternating voltage at high current to high alternating voltage at low current. Right? Simple. It is used for conversion of current. Fine. Do we get this thing clear? Right? Now, how do I construct a transformer? You would have a strip, a rectangular metallic strip, this is your metallic strip on which you would have two coils that would be wound. One would be called as the primary. Here you have a coil that is wound on this, and then you have another coil that is wound on this. Right? So you have coil wound on one arm and the other arm. Right? This would be called as your primary, and this would be called as secondary. Fine. So a transformer consists of two sets of conducting as well as insulating wires. It consists of two sets of conducting as well as conducting and well insulated wires. Right, I have two wires, one and two sets of wires, and both of them are very well insulated, wound upon separate limbs of a soft iron core. Wound on separate limbs of a soft iron core. This is your soft iron core. Right? These are the two limbs on which they are wound. One is bound on one and the other is on the other one. Right? One of the coil is called as primary and the other is called as secondary. One of the coil is called primary and the other is called secondary. Fine. Now, once you have this, the soft iron core acts as a support to the primary and secondary and also helps to increase the magnetic flux linked with the coil. The soft iron core acts as a support for primary and secondary and also helps to increase the magnetic flux linked between the coil. Helps to increase the magnetic flux linked between the coils. Fine, do you get this in here? Now, AC voltage is applied across the primary of the coil, primary coil of the transformer, and when the transformed output is obtained across the secondary. I can say AC voltage is applied to the primary coil and transformed voltage is obtained at the secondary. You're going to give input to the primary and you're going to take output from the secondary. Now the two coils are electrically insulated but they are magnetically linked, right? The two coils are electrically insulated but magnetically linked, right? And in order to reduce the eddy currents which will produce excessive heat, the soft iron core is made up of laminated sheet and is coated with insulating varnish. In order to reduce eddy currents, the soft iron core is made up of laminated sheet sheets and coated with an insulating varnish. Right, do we get this in here? So that's how you construct a transformer. That's your construction of the transformer. Fine, do we get this in here? Right. We'll stop this here for the day. Thank you very much.